What is implicit differentiation? In elementary calculus, you learn about implicit differentiation. One of the popular examples in elementary calculus is calculate the rate of change of y with respect to x directly from the equation of the unit circle x squared plus y squared equals to 1. In that case, when it's written implicitly like this, we usually assume y is a function of x. So you're basically rewriting this as x squared plus y of x to the second equals to 1. Now, we take the derivative of each term. The derivative of x squared is 2x plus the derivative of yx to the second power using chain rule. On the right-hand side, you have the derivative of 1, which is 0. Basically, you have the derivative of yx to the second power with respect to x. Using chain rule, it is 2y, y prime. Now let us do the substitution. This becomes 2x plus 2y, y prime equals to 0. Now let us simplify this. Subtract 2x from both sides. You get 2y dy dx equals to negative 2x. And then divide by 2y, assuming y is not 0. dy over dx becomes negative x over y. Again, assuming that y is not 0. So this is the rate of change of y with respect to x. This is what we learned in elementary calculus. But take a look at this relation. We can build a two-variable relation between these two and apply implicit differentiation theorem. Suppose that f of x and y is differentiable and that the equation f of x and y equal to 0 defines y as a differentiable function of x. Then, at any point when the partial derivative of f with respect to y is non-zero, the rate of change of y with respect to x is negative partial derivative of f with respect to x divided by the partial derivative of f with respect to y. Basically, if you write f of x, y, and z equal to 0, this z is nothing but a relation between x and y. So you are writing a relation between x, y, and f of x and y. And on the right-hand side of the relation, we usually have a 0. So if you were to take the derivative, you have the partial derivative of f with respect to x times the partial derivative of x with respect to x plus partial derivative of f with respect to x times the partial derivative of y with respect to x plus partial derivative of f with respect to z times partial derivative of z with respect to x. But note that partial derivative of x with respect to x is always 1, and partial derivative of y with respect to x is equal to 0. So it helps us to simplify this as much as we can. Here you have a 1, and this guy is 0. So the whole middle term disappears. You end up with partial derivative of f with respect to x plus partial derivative of f with respect to z times partial derivative of z with respect to x. On the right-hand side, it is 0. So you can simplify this. The partial derivative of z with respect to x, you can isolate this on one side. On the right-hand side, you get negative. This is f of x, partial derivative of f with respect to x, divided by partial derivative of f with respect to z. With the same logic, if you take the partial derivative with respect to y, partial derivative of z with respect to y is negative partial derivative of f with respect to y divided by partial derivative of f with respect to z. But this is how you get to these relations. It's not that difficult to see, you can easily take the derivative with respect to x, y, or any other variable available. In this example, question says, suppose you have f of x and y and z defined this way. What is the graphical interpretation of these partial derivatives? Remember that we are taking the partial derivative of z with respect to x, partial derivative of z with respect to y. And we have a point that has x1, y1, z1. Partial derivative of f with respect to x, it means that y and z are constant. So you're basically have x squared, the derivative is 2x, this guy becomes 0, y squared, derivative is 0, 2z, well, it is going to be 0, then you have 12x, which is 12, and the rest are 0. Partial derivative with respect to y, out of all of these terms, we only have one y, which is y squared term. So you get 2y out of it. And for f of z, you have negative 4z minus 8, because your z terms are just here and here. The rest are constants. Now, the partial derivative of z with respect to x, following the formula, is negative partial derivative of f with respect to x divided by partial derivative of f with respect to z, which is 2x plus 12, divided by, if I just distribute this negative sign in f of z, it becomes 4z plus 8. The derivative at p, 1, 1, and 1, it means that x, y, and z are given to us. This is this point just right here. Is 2 times 1 plus 12 divided by 4 plus 8, or 7 over 6. So the rate of change of the function with respect to x is positive. Now the partial derivative of z with respect to y, following the formula, is negative partial derivative of f with respect to y over partial derivative of f with respect to z, which is 2y divided by 4z plus 8. Again, this negative sign is distributed on the denominator. That's how you get a positive 4z plus 8. Plug in 1 and 1 and 1, you get 1 over 6. Again, you have a positive rate of change. This rate of change is a little bit more faster than 1 over 6.